Hello and welcome back. In this video we'll be looking at section 7.5, and technically section 7.5 only really covers the dot product and some uses for that, but I think it's important to cover cross products, which are a different type of way of multiplying vectors that isn't mentioned in the book, so I've included some resources from outside of the textbook for this section. So in the last section we saw that vectors are defined with a direction and a magnitude. So you have to say what direction is the vector pointing in and how long is that vector. So we just think of vectors as an arrow. But if we're drawing an arrow, we can give that using coordinates as well. So for instance, we always use the origin as the initial point of a vector, just to make it standard. But if I draw a vector and I wanted to tell you what direction it was pointing in and how long it is, all I need to do is tell you that endpoint. So if this endpoint was 2, 1, we know that it starts at 0, 0, so we can figure out exactly how long that line is, and we know what direction is pointing in, because I know this coordinate. I can graph those coordinates, I can draw an arrow between them. This is just a nice way of describing vectors, is to give the coordinates rather than saying, oh, it's at this angle and it's this long. And this can be done, pretty much anywhere. So we can have, say, like -1, -3 as another vector where I'm giving it in terms of the coordinates. Now, when we give vectors in terms of coordinates, we don't use the round brackets, the parentheses, because that represents a point in space. If we want to represent a vector, we use these angled brackets. And in doing so, we know that it's going to be a vector. It starts at the origin and ends at essentially the same coordinate. So this vector would start at 0, 0 and goes to the point x, y. So it's a vector that points from the origin to x, y, and we give that information that it is in fact a vector by adding angled brackets. So far this semester we've only really worked in 2 dimensions, but this works the same in 3 dimensions or more as the case may call for. So we would just give x, y, and z as the coordinates instead of just x and y. But everything works the same in 3 dimensions. So what we saw last time was scalar addition scalar multiplication and addition. So you can take a vector, we can take a vector v, and we can multiply it by a constant. So if v was something like this, 2v is going to be something like this. We just multiply the length by 2, but it's still pointing in the same direction. When we talk about this in terms of coordinates, scalar multiplication and addition as well, so when we add vectors v and w, we draw our parallelogram, where that's just going to be another copy of w, that's going to be another copy of v. The sum, the resultant, is this angle starting, is the vector starting at the beginning and ending up here. So we could draw pictures of all these last time, and while that was kind of helpful, giving things in terms of coordinates is a lot easier to work with. So now that we've done it the hard way, we can do it the easy way. So if you're given a vector x, y, and we want to multiply it by a number, we just multiply the coordinates by that number. So c times the vector x, y is just the vector cx, cy. Also, if we want to add vectors, and we're giving it as the coordinates x1, y1, and x2, y2, we add the x coordinates and we add the y coordinates. So it's x1 plus x2, y1 plus y2. And that's it. This is the easiest way to do vector addition and scalar multiplication. So let's just do a bunch of examples, because I think that this will be the easiest way. So we have u as the vector 5, 2, and v is the vector 1, -3. So let's find 2u. Well, this is the same thing as 2 times the vector 5, 2. And all we do is we're going to multiply each coordinate by 2. So we have 5 times 2, 2 times 2, which is going to be the vector 10, 4. And that's it. So multiplying a vector by 2 just means multiplying each coordinate by 2, which is fairly straightforward. To add vectors, so let's take u plus v. So this is going to be the vector 5, 2, plus the vector 1, negative 3. And so all we're going to do is we're going to add the x coordinates together, and then we'll add the y coordinates together. So let's add 5 and 1, and then we'll add 2 and negative 3. 5 and 1 gives 6. 2 and negative 3 gives negative 1. And that's it. So when we add vectors together, we get another vector. Yep, we have that. And then the last one, we have 3v minus 4u. And for this one, again, it's everything should essentially just fall out, come out in the wash, because we've got 3 times v, and v was 1, negative 3, minus 4 times u, which u was 5, 2. So let's distribute our scalars out front, our numbers. So this is going to be 3 times 1 and negative 3 gives 3 times 1 is 3. 3 times negative 3 is 9. And then we'll subtract, okay, 4 times 5 is 20. 4 times 2 is 8. And when we subtract vectors, okay, so we've got 3 minus 20 is negative 17. And negative 9 minus 8 is also negative 17. So again, there's not a whole lot going on when we multiply vectors by a number or add vectors together. When it's given in terms of coordinates, this is pretty straightforward. We just multiply, we just distribute the scalar out front, and we combine x and y values as they come up. So all of that is pretty good. What I want to do now is introduce one more way of writing vectors, and this can be a lot very, very helpful in some situations, but can also be a little bit cumbersome. It's just more notation. So when we're talking about vectors, some of the most basic vectors that we can talk about, and these are called basis vectors, are the ones that are pointing in the x direction and the y direction. And rather than pointing, and just any arbitrary amount, what we're going to do is we're going to take the vector that points exactly 1 along the x-axis. So this point here is going to be 1, 0. And this vector is called I, and we draw it with a little hat. So the hat means that it's exactly 1 long. It only stretches from the origin 1 in that direction. The one that would go in the y direction, so it would stretch up from the origin to 0, 1. This is called j hat. And again, these vectors, we can write I in terms of these coordinates. So we can write I as 1, 0, and we can write j as the vector 0, 1. So these are somehow really nice vectors to work with. And in 3 dimensions, we have 3 basis vectors that we'll work with. We've got I, which will stretch in the x direction, 1. And again, no, I always stretches in whatever the x direction is. So in a 2-dimensional drawing, the x is always to the right. In a 3-dimensional drawing, x is sort of coming out of the page toward us. The j vector is going to be pointing in the y direction. And then ij, k is pointing in the z direction, which will be pointing straight up. And that's all there really is to it. So I is 1 in the x direction, j is 1 in the y direction, k is 1 in the z direction. And we can go back and forth between these two forms as well. So for instance, this vector points 6 in the x direction, it has no length in the y direction, and points sort of -1 in the z direction. meaning it's going to point down instead of up. So here, if we point 6 in the x direction, that's like 6 times the usual I vector. If we're pointing 1 in the x direction, that's just I. If we're pointing 6, we've got to multiply it by 6. We're pointing 0 in the y direction, which is j, and we're pointing -1, so down 1, in the z direction, which is k. And again, I can simplify this. 6 times I, we can just leave that. 0 times j, 0 times anything is just going to be 0, so I might as well not even consider that. And 1 times k is just k, so this is going to be 6i minus k. So this is just a nice way of writing this guy down. There are times when this will be useful. I think I prefer the coordinates, though. This is the way that I would prefer it, but it's important to know both. And then with this one, if we have 5i plus 2j, again, that's going to be pointing 5 in the x direction and 2 in the y direction. And since we're not talking about k here, I'm just going to assume that this is a two-dimensional vector, and I'm not going to put a third coordinate down. If we're not talking about 3 dimensions, why even include that third dimension? So we can go back and forth between thinking about things in terms of these coordinates and thinking about things in terms of I, j, and k. But let's do some examples where we add these vectors together and multiply them by scalars. And I want to do this in terms of the i's and the j's. So if we want to find the vector 3 times u, it's going to be the vector 3. It's going to be 3 times the vector -I plus 6j. And this works about how you would expect. We essentially distribute the 3. So instead of pointing -1 in the x direction, it's going to be pointing -3 in the x direction. Plus 3 times 6 is going to be 18 in the j direction. And that's it. All we do is we just distribute those numbers. Let's find u plus v. So we've got -I, we need the hat there, plus 6j. And we're going to add this guy, which is 4i plus 2j. And again, what we want to do is we want to combine like terms. So we've got some i's, so let's add those together. So we've got a -I and a 4i, so when we combine those together, we get 3i. Here we've got 6j's, here we've got another 2j's, so that adds up to 8j's. And that's it. That's all there is to adding these vectors. Let's do one more example. We've got 2v minus u. So we're going to take 2 times the vector v, and we're going to subtract u. Okay. So the first thing I want to do is distribute this 2 over here. This is going to be, we'll have 8i plus 2 times 2 is 4j. We're going to subtract -I plus 6j. And we've got 8 i's, and we're going to subtract -I. So subtracting a negative number, we're going to add 1. And then we've got 4 minus 6. And so it's going to be minus 2j. So again, writing these things in terms of I and j is maybe to me a little bit less useful or less helpful than just writing the coordinates down, but ultimately it works just how you would expect. In the next video, we'll see how to multiply vectors.